Module 3 is History and Science, and Module 3-1 is Science. I'm going to try and explain something about what science is in this unit. The scientific method is to make a prediction and test something. It's basically you never just accept something. You find out if it's right, you do some tests. This gets scientists into trouble with their friends because their friend says, hey, that's going to happen this way. And then you say, how do you know? And your friend says, what, you don't believe me? But this is sort of my nature is, how do you know that? I need to know how you know it before I can know it. Well, much of science is testing theories. So you have an idea, it's a pretty well explained thing, but you want to fully test it. And that's what a lot of scientific work is about. Science is not a bunch of facts, but it is a lot of theories that are networked together. When you say, I have a theory, you're not meaning a scientific theory. You usually mean, I just thought of something that might be true. Well, a scientific theory has a lot of details, and it's well tested. And it has within it some hypotheses. A lot of times when something's a simple little hypothesis, an untested theory, people will say that's their theory. And if you have a couple of theories or hypotheses to choose from, Occam's razor says, try the simplest one. It's probably the correct one. So a scientific theory, as opposed to, hey, you know what my theory is? All right, a scientific theory has too much detail to sum it up in one sentence. Even if you can, the theory itself has a lot more details to it than that. And a very important thing is, it makes predictions that can be tested. Or some people will say, it's falsifiable. You may not be able to prove it's right, but you have to be able to prove it's wrong if it is wrong, or it's not considered a scientific theory.
For me, what the best definition of science, or the scientific method that I've heard, comes from a very famous physicist called Richard Feynman, who won a Nobel Prize for building one of the first quantum theories of electricity and magnetism. It's called quantum electrodynamics. This is back in the 1940s and 50s. It's our best theory today of how light interacts with matter. But Feynman was also, I recommend that you read his books. He was a brilliant teacher, a brilliant lecturer, as well as a Nobel Prize-winning physicist. And he gave this lecture back in, I think it was the 1960s, and it's just a 1-minute definition of the scientific method.
I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we no, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
So I think that's a really beautiful description of what science is. It's really very simple. It's the application of common sense in many ways. What it is looking at the universe, looking at nature, guessing about how it works, seeing what the consequences of that guess are, testing those against nature, and as Feynman said, the great power of science. It doesn't matter who you are. There's no such thing as authority in science. If your guess disagrees with nature, then it's wrong, and that's all there is to it.
A good scientific theory, it has to be able to make predictions. In fact, if it doesn't make testable predictions, you don't even get to call your idea a scientific theory. It has to be testable. You have to have a way that you can prove that it's wrong, if it is wrong. And if there's other theories, it really ought to conform to those theories. If it conflicts with other things that have really been thoroughly tested, then that theory is looking pretty weak. A theory is its main duty in life is to explain observations so that it can be predicted. And you have to discard that theory if it fails tests. You're allowed to modify it, but if it's predicting one thing and you're observing another, chances are that theory is incorrect. On the other hand, you can never prove a theory is true, so be careful of this. I'm going to emphasize this. You can't prove it's true. Theories are never proven to be true. I'm sorry, it may be sad, but it's true. All of science is things that we are assuming for the moment. They may be well tested, but we recognize that in the future they could be proven to be wrong. What's the prediction in this sentence? Moon rocks must have a high lactose content because the moon is made of green cheese. What's the prediction? And what's the hypothesis? The hypothesis is the moon is made of cheese, and from that you conclude, or you predict, moon rocks have lactose. One thing you're assuming, and what does it predict? This is a lot of times the way you could recognize that. If this is true, then this is true. If, here's my hypothesis, then this is what's predicted. Because remember, a scientific theory, even if it's a simple little sentence, should have a prediction, a possible prediction. Here's that same sentence written in the if hypothesis, then prediction. Good support for a theory, confirmation of a prediction after it's proposed. You can explain everything you want, but a good theory will be able to predict things that you have not yet observed. We'll be hearing about that in the Big Bang Theory, when an amazing prediction turned out to be correct. True or false? A theory that's proved true is a law. Something to be considered in science is what we call in astronomy the selection effect. And in other fields they call it a sample bias. The problem is a lot of times you'll have a sample and you statistically show something from your sample, but you don't have a good sample. If you have a biased sample, your results don't relate to the general population. For example, if you study the 50 brightest stars in the sky and you're trying to find out how many spectral types there are of each type, you'll be way off because the brightest stars are a biased sample. They happen to be the ones that are brighter for some other reason, and that would actually affect your results completely. Let's say somebody says, I know the average age of people. I took this college class and asked all their ages. It's the kind of biased study that people actually do. This is not very subtle, but you get the idea. I've seen this question, what % of your shopping is done online? Except for the question was on the web when I was looking at an online vendor. So if you want to know what % of the shopping is done by people who are already shopping online, that's a different answer than the general population. I think they just wanted me to click there, but still. Well, Einstein said, pure logical thinking cannot yield us any knowledge of the empirical world. All knowledge of reality starts from experience and ends in it. So you better get yourself some observations, some data, before you know what the world is like. So why isn't this a scientific hypothesis? Space is permeated with a substance that is undetectable. Yep, what's the prediction from there? I predict I can't find anything. So that can't be tested. It makes no testable predictions, so that can't be considered a scientific hypothesis. Now, which of these is a scientific hypothesis? We're surrounded by life forms from a different. In summary, Module 3-1 about science, we talked about what is a scientific theory, and one of the points is that when someone says, my theory, or I have a theory, that's different than a scientific theory, which is well tested and could be proven wrong if in fact it was wrong, because it makes testable predictions. So the phrase, oh, gravity, that's just a theory, oh, the Big Bang, that's just a theory, shows that the person talking doesn't have a full grasp on a scientific theory, as opposed to, I have a theory, which is not referring to something that's well tested and interlocked with many, many things that we know, and makes predictions that can be tested.